Okay, this projector is warming up here, and while it does, we all heard, before you even read anything yesterday, I'm sure we've all heard the term acceleration before, right? So, in your own words, nothing fancy, how would you explain to me what something that is accelerating might be doing? There's actually three things it could do. Give me one, yeah. Good, speeding up. Once this comes up here, that's one of the first things. The opposite of speeding up is slowing down. And the last one might be surprising. We'll get to why. It's changing direction. So, like I said, if you want to write these down, that's absolutely okay. I'm going to post them right to Google Classroom. This is the first time I put notes up on Squid. That's what I always do. They'll be titled on Google Classroom. They'll just go to their own posting on Google Classroom. And it'll just be called class notes, whatever the day I gave them. Just so you guys know. I try to limit the notes, but sometimes there's just stuff I want to put extra. The worksheet went over all this, but asked it in a more roundabout way. So I have a little thing up the side of these two. So these are all the three ways to accelerate. Change mag, I just abbreviated that for magnitude. Remember, guys, magnitude means size, right? We learned? So if I asked you what the magnitude of acceleration is, that's going to be the number we actually attach when we give it as a value, okay? So how in the world is changing direction? Changing direction seems a lot different than those two, right? But now we're going to go to the definition of acceleration. If you look up in any book, science book, whatever, physics book, the definition of acceleration, it'll say something like this: the change in velocity over a period of time. And we already hopefully remember what velocity is, right, guys? All right. So if you go back to last week, we learned that velocity is a vector, right? So it cares about what? Direction. Acceleration is also a vector, by the way. It also cares about direction. But, so an example of a velocity would be like a car going 25 miles per hour north down the road, right? That's an example one because it gave magnitude and direction, right? So now let's go, now that we know the actual definition in words from acceleration, let's go back to what we listed and look again at the three ways to accelerate. So obviously, if you speed up, you're going to change your velocity, right? The definition was a change in velocity over time. If I slow down, that's going to change my velocity, right? It'll change the number. So if I was going 25 miles per hour north and I sped up, now I'm going maybe 30. That obviously changed my velocity. Or if I slow down, now I'm going 20, right? So that clearly changed it. But this one right here changes it for another reason. Let's pretend we're on the highway on cruise control. Cruise control holds your speed steady. But does cruise control hold your velocity steady necessarily? No, because you could go around a turn, right? If you go around a bend or a turn, doesn't that change your direction? So since acceleration is changing velocity over time, a third way to change your velocity is change the direction. You could do 2 out of 3 of those at one time. So if I'm not on cruise control and I'm holding the gas and getting faster and faster and faster, speeding up essentially, and turn, I could have 2 different types of acceleration at once. Now, these two matter the most to us for the near future. Since the kind of physics we're studying early on being mostly one-dimensional stuff on one axis, these are the two that matter the most, but you should know there's 3 ways. And this way we'll get to a particular topic called circular motion a little bit down the road and focus on that one. All right, so these two are the most important ones right now, but at the very least know that there's 3 ways, okay? So with that in mind, we're going to say a few other things. Units. You're probably pretty unfamiliar with this type of typical units for acceleration because they're not going to be like meters per second. Meters per second will be for speed or velocity. All right? They've got to be different. If it's a different idea, then it's got to have a different unit. There's 2 most common units. These aren't the only units. In the worksheet, you saw some other ones. All right? But as the year progresses, when we talk about accelerations, we'll mostly see these units. Actually, this is just 2 different ways to write the same unit. Meters per second or meters per second squared. All right? Let me give you an example of using this rather than just showing them to you and say this is it. All right, let's say I'm going to walk towards that wall speeding up the whole time, okay? So I'm going to get faster and faster and faster and faster until I can't anymore because the wall's in my way. So from there to there, I got pretty much faster and faster, right? I didn't go steady, did I? I did not have a constant velocity. If I had a constant velocity, what would be my acceleration rate? 0, right? Because if I go at constant velocity, never change direction, then I have 0 acceleration, right? But I did speed up. So let's say I'm just going to make up an easy number. Let's say I accelerated at a value of 2 meters per second per second. We could also say that as meters per second squared, but it's better understood thinking of it this way. We actually technically write it that way more often, but it's better understood thinking about it as the less condensed meter per second per second. Because if I tell you that I'm speeding up at 2 meters per second, that means every second that passes, I speed up by how much? What was the number? What number did I just say? 2. All right? If I tell you, I'm just telling you this. Just take my word for it. I was speeding up. I was accelerating, in other words, at 2 meters per second per second. That means every second that passes, I speed up by 2 meters per second. Meters per second per second. Does that make sense why that's the unit? Every second that passes, I speed up or slow down. I'm using the speed up example now by that much. All right, so we could easily get a pattern here with simple numbers. So if I start from rest, guys, and 1 second passes, I'm going 2 meters per second. But I'm still continuing to speed up at the rate of, after another second passes, I'm going how fast now? Every second I gain 2. So the next second I would now be up to 4. The next second I would be up to 6. As long as this is a uniform acceleration rate, and that's the kind we study in here, okay? All of our accelerations are going to be assumed uniform. Why? Because it takes a lot more difficult math to handle non-uniform acceleration, okay? Like, let me give you a real-world example where uniform acceleration could occur. If you're on a flat road and going straight in your car and holding the gas in steady, not going like this, holding it steady, your car, you're giving it like a steady amount of gas, like the same rate of it was translated in your engine to a steady increase. All right? So you would have a uniform acceleration, we would call it there. All right, but if you were in your vehicle and hitting your gas pedal like this, you'd be all like this, right? Like a jerky motion. That's because you would have like non-steady acceleration. We're going to focus on steady, or what we call uniform acceleration. So those are the 2 most common units, especially as we move along in the year. All right, the next thing is pretty important. For the second side of your worksheet, hopefully you got an understanding of it from reading through the website, but let me throw out a question real quick for you because I flash up the other part. Let's say that I'm looking out the window, but you guys aren't, just like right now, okay? And I see the road just outside, and I have an accelerometer in my head that I can look at anything and tell you what its acceleration rate is. And let's say I tell you guys don't see it, that I just saw a car accelerate at -5 meters per second squared. What do you think that car is doing? If I tell you the acceleration was -5 meters per second squared. Is it in reverse? That's probably that's the most common answer we usually get. Usually somebody either says it's in reverse or they say that it's slowing down. But actually, I just gave you a trick question because I didn't give you enough information. Here's what, to know if a car is speeding up or slowing down, you have to know what direction it's in anyway. So actually, I could give you a negative acceleration, but it'd still be going in the positive direction. I'll explain how in a second, okay? So I'm going to use myself after just walking to explain that in a second. All right, but here's the deal. You actually have to know both the sign of the acceleration, the direction of the acceleration, and the direction of the velocity. Did I ever tell you which way the car was going, guys? No, I just said the acceleration is. You need to know what the current acceleration or current velocity is, direction-wise, and then consider the direction of acceleration. That decides if the thing's speeding up or slowing down, okay? So just the acceleration alone doesn't tell me if it's speeding up or slowing down. I have to know some other stuff, unless I'm straight up literally told it's speeding up or slowing down. So, anyways, here's another thing before I use this example we need to understand. This is is actually going to be essentially one of Newton's laws later on. Let's take this blue ball that's sitting right on my table. Nothing's touching it. We could stare at it all day, and if nothing's touching it, will it do anything? So for that ball to accelerate, or it to maybe speed up, since that's one way to accelerate, what would have to be applied to it? Something would have to apply a what? A force. Good. Now, forces are for a later day, but we need to at least mention them right now. Forces are what cause accelerations. Accelerations don't magically happen. All right? So if we were sitting here all staring at that ball and just popped up in the air like magic, we'd all be pretty scared, probably. I'd leave and lock you in here. Anyways, a force we would expect has to come do that, and it does. So for my example with these, I'm going to walk this way. But we're going to define, this is important, we're going to define this way as positive and this way as negative. Okay? So, if I'm walking in the positive direction and you want to speed me up, all right? If you were to push me, if I'm walking this way, which is the plus direction, and you want to speed me up, would you push me from behind or in front? From behind. If you push me from behind, you're applying a force on me that way. Remember, forces cause accelerations. And if you do that, you're actually accelerating me in what direction? What direction did I call that? The positive. So that goes along with this. If I'm already going in the positive direction, and something or someone or somebody or somehow, some force applies a positive acceleration to me, I will speed up. But what if I was walking in the negative direction? This way is the negative direction, right? And you wanted to speed me up. Now you would push me in the back still, and that would still be the negative direction, right? You'd push me, I'd speed up that way. I'd fall forward. So even though now I have a negative acceleration, I still could be speeding up. So a negative acceleration doesn't have to mean slowing down. It depends which way I was going in the first place when it was applied. Does that kind of make sense? All right. Now we do the opposite, slowing down. Now I'm back to walking in the positive. There's only 4 scenarios. These are all 4 of them that could happen in 1D motion. If I'm walking in the positive direction again, you want to slow me down, which way are you going to push me towards? This way, towards the negative. You can get in front of me and push me that way to slow me down, right? Opposite, right? If I'm going one way and you want to slow me down, you better apply the acceleration the other way. So the sign of the current velocity of the object is opposite in sign of the acceleration you're slowing down. You can go opposite either way. I could have been walking this way. And then if I'm going in a negative direction to slow me down, you would have to accelerate me positively, right? Put the force that way. Because the force and acceleration will always be in the same direction. So that's how we tell, if we weren't straight up told, that's how we tell in a situation if something's speeding up or slowing down by knowing values. And the whole backside of the sheet from yesterday had stuff like that. If we remember that, those questions will be pretty easy. All right, so that's the gist of all general stuff, other than a little formula we might have to apply. All right? There's this formula. This is just the acceleration equation. And this is a condensed way to write it. This symbol, is anybody familiar with a symbol in math that's a triangle and what it means? If not, anytime you see this in any kind of equation, a triangle, it means change in. Remember why we just defined acceleration, guys? Acceleration is a change in velocity over time, right? This is the mathematical way to say that we defined in words earlier in the notes. But the reason why I boxed this is the expanded version of it. This is the useful version of it, okay? So if I have actual numerical values, and for example, some of you may have seen car commercials before, especially for sports cars, stuff like that. Yeah, the car manufacturers and engineers understand that the majority of people out there probably never took a physics class. So they don't tell you and try to brag about the acceleration rate of a car in a commercial using a unit like meters per second squared, because the common person wouldn't have any idea what that means. But leading up to it, somebody could understand it. If you ever saw a commercial where it said this car could go 0 to 60 in like 4 seconds, did everybody like hear that, paying attention to a commercial before? If you didn't, that's okay. But that's a very common thing, especially because obviously, even if you don't understand that they're telling you about acceleration, comparison, if you had one car that could do 0 to 60 in 3 seconds and one car that could do 0 to 60 in 4 seconds, which could accelerate faster, the one in 3 seconds or the one in 4? Yeah. 1 in 3 seconds, right? So that must be better, right? But we can figure out as a single number. We could actually plug in those values into this formula. 60, if it goes to 60 miles per hour. Why they pick 60, I don't know. That seems to be the standard. If we got up to 60 miles per hour, that would be the final velocity. That's what that VF stands for. And this is initial velocity. Well, if it started from rest, 0, right? That would be 0, divided by how long it took. And then we can crunch the numbers and get all one number with 1 unit. And we will do that on the study guide. You guys had to do it, try it yesterday. Just one thing on the study guide, and this is kind of weird because later on they call it initial. Initial and original mean the same thing. On your study guide, they called it V original, but actually more commonly it's called initial. No big deal. Both means the same thing. All right, so that's a quick summary of what you need to know for acceleration. Hopefully you got some of this right. Fix whatever you didn't, or at least look at the key that I will post before the quiz tomorrow. Okay? Let me flip over to the key, and hopefully anything that didn't make sense yesterday from you looking it up on your own will now. I don't really care about the review questions for right now. Let's go to the concept of acceleration. In number 1, it basically says, now that we know the 3 ways to accelerate, what are 3 functions in a vehicle that could cause those? All right. What could cause it? Obviously, cause your vehicle to speed up, guys. The what? The gas pedal, right? The sometimes it's referred to as the accelerator, right? Because of that. What could cause your car to slow down? The brake pedal, right? And what could cause your car to change direction? The steering wheel. So all those account for the 3 ways your vehicle could do any forms of the accelerations we talked about. Yeah. Can you? The deal with gears is this, and we'll talk about it much more later when we get to something called rotation and torque way later in the year. It doesn't matter what gear you're in if you never hit the gas pedal, right? So it technically wouldn't accelerate you. The gas is what does it. The gear is what changes and varies your torque, right? And what that means, we got to dig a little bit more into. You might have a general understanding of torque, but some out there might not. So I don't want to explain that now, but that'll come later. Right? But,
first gear is because, like, when you let the clutch out in a manual, your car will start to coast on its own while you're in first. That's why I was saying.
it may a little bit, but let's just go simple for now, and we'll talk a lot more about that later. Okay? Because we could get into gears and gear ratios, and gears give us what we call different mechanical advantages, and there's trade-offs with them and stuff like that. But let's just keep it simple for now and go gas pedal, brake pedal, steering wheel to answer that one. All right, number 2, I'm going to go through a little more quickly for some of these so we can get through them. So number 2 just says that an object is accelerating if it's moving. When it says circle out of the apply, that means there could be more than one right answer. Doesn't have to be, but there was. A and D are the only ones that fit into how we define acceleration and the ways to do it. Changing speed, that could mean speeding up or slowing down, right? And we said those are 2 forms. Or in a circle, which in a circle you're constantly changing what? Direction. Now, before I move on to the next one, for some reason in the past, it's very common for students to think this is one of the right answers. Extremely fast. So just in case anybody put it out there, because often somebody puts that as what they think is the right answer. Just because you're moving extremely fast, do you have to be speeding up, slowing down, or changing direction? No. You could be in a rocket sled thing that reached its max speed, going in a straight line. You might be going crazy fast, but at that moment, you don't necessarily have to be accelerating, right? So just extremely fast. Yeah, to get there, you would have to accelerate, but that's not what it's saying. Just that alone doesn't mean you're accelerating. Just those 2 answer that. And just be very careful with number 3, because it says one knows for sure. That means 100%. Not could be, that means for sure. So if an object is not accelerating, then one knows for sure that is B and D would fit what we define acceleration as. Moving with the constant speed. If I'm not accelerating, I would know for sure that my speed's constant, right? Because if it wasn't, I would be accelerating, right? Because I'd be speeding up or slowing down. And I would also have to say maintaining a constant velocity would have to be true. if I'm not accelerating, because if I change direction, doesn't that change my velocity? So that would have to be maintained. The one that's sometimes accidentally wrong with some, and I see why, is at rest, because it says for sure. If you weren't accelerating, you could be at rest, but that's not 100% true. It's a possibility, but not for sure, because I could just say I'm not accelerating, but something's on cruise control going down a straight road. All right, and that's not at rest, right? So these are the only two that would have to be true if we know for sure we're not accelerating. All right, there's the formula that I told you. And these first couple questions focus on the unit itself, the meters per second squared or variations of other common acceleration units. So, in number 4, it says an object with an acceleration of 10 meters per second squared. We'll circle all that apply, but there's actually only one right answer. This is very similar to the example I gave you of me walking and speeding up. All right? If I tell you 10 meters per second squared, remember, if something's speeding up, or actually, it doesn't say speeding up or slowing down, does it? So it could be doing either. So if I say it's either speeding up or slowing down by 10 meters per second squared, that really means 10 meters per second per every second. That's what meters per second squared means. So I basically said the answer there to us then. What that means is it changes its velocity by 10 meters per second every 1 second. 10 meters per second per second. Make sense? Now, often this one is picked, and I see why, because it's tricky. Had this question told us that it started from rest, in 10 seconds it could possibly reach 100 meters per second. Possibly. Okay? Because if every second 10 was added, after 10 seconds you'd be up to 100, right? But that's assuming something. We're not allowed to assume stuff like that. It never told me it started from rest, so maybe it was started acceleration when it already had a certain speed that wasn't 0. If that's the case, then D wouldn't have to be true. All right? So B is the only true answer based on what we were told there. All right, number 5. This is just not using the equation yet, but seeing an easy pattern. So somebody is increasing, so we know we're speeding up because it tells me that. And we know we're from rest because it says we're going 0 miles per hour at 0 seconds. And then at the 1 second mark, I'm going 10 miles per hour. At the 2 second mark, I'm going 20 miles per hour. At the 3 second mark, I'm going 30, then 40, and so on. The obvious pattern here is that every second passes, I'm increasing by how much? Every second that passes, what is my speed increasing by? 10, right? So now it wasn't meters per second, though, was it? So we could use the units here. And this is a valid unit as well. 10 miles per hour per every second, right? Isn't that what that's showing? It's increasing by 10 miles per hour per every second. Now, we can't condense those units because it's hours and seconds. We would leave them like that. But any distance, like mile unit, okay, and time unit, like hours or second, any distance per time unit would be a valid acceleration unit. Maybe not the most common one, because meters per second squared or meters per second is. But that's still a valid one because it's a distance per time unit. All right, the next couple use this little formula. And for this quiz coming up in this unit, we will not have a need to rearrange this formula. Remember, we had one other formula last week. And by the way, formulas will be given to you in the quiz if you need them. They'll be up on the board if you need them. You don't have to memorize them. You just have to know how to use them. Now, the V equals D over T formula from last week, we said you might have to rearrange that one algebraically if necessary, and we did that on the study guide. For now, this one we're going to only use straightforward, if at all. So that means it's solved for acceleration. We're only going to use it to find acceleration for now. Later on, a few weeks from now, that might not be true. We might be rearranging it, okay? But so all we got to do is look at the numbers and pop them in. So here's a car, like I said, going from 0 to 60 in 4 seconds. 0 is what it starts at, right? 0 miles per hour to 60. So 0 is the original velocity, right? Or initial, means the same thing. 60 would be the final, right? And 4 seconds is obviously the time. So we just pop into that simple equation. 60 minus 0 is 60, right? Divided by 4 is 15. 15, what's the units? We'll look at the units that were used in the problem. Miles per hour per second, right? Make sense? Just popping numbers into that. You'll have a calculator if you want tomorrow, okay? All right, number 7. Plugging in numbers again. The car speeds up from rest. From rest means what? Obviously. Someone stop. 0, right? So V initial 0. We get up to 16. That's speed final in 4 seconds. 16 minus 0 is 16, divided by 4 is 4. Just look at the units. This time it is meters per second, because the original ones were given in meters per second, divided by something in seconds. 4 meters per second squared. We good? Stop me if something doesn't make sense, and I'll re-explain it, all right? And another one, just one more here. A car slows down from 32 to 8 in 4 seconds. So 32 is the initial, 8 is the final. When we subtract those, you're going to get a negative number. Divided by 4, you're going to get negative 6 meters per second squared, plugging into that formula. And in this case, it clearly does mean slowing down, because originally this car was traveling in the positive direction. When you hit the brakes, the force on the brakes between the friction in the road and the tires have to be opposite of you to slow you down, right? Which should make sense why, if we were going positive, the acceleration that's spit out is negative. Because the brakes is what slows you down. The brakes latch on to the rotors on your wheel, and that starts the process. But what truly slows your whole car down is your tires in your road, right? Because if you slammed on the brakes on ice, yeah, your rotors are still going to be clamped on with your brake pads, but you're still not going to stop if you're on ice, right? What really stops you is the friction between the tires and the road after that process. That'll be talked about a lot more later on. Friction's a big topic later. All right, any questions on the front? All right, on the back side. Tell you what, since we're low on time, number 10, I wanted you to do everything. Number 10, don't worry about. Sometimes that diagram confuses people, and it's the same idea as the stuff above. All right? So, especially if we're run out of time here, don't worry if we don't get to number 10. If you understand number 9, then you got the idea for anything that could be possibly on the quiz, okay? All right, so with the idea in mind, if I know I'm going one way, and if it tells me I'm speeding up or slowing down, then the acceleration has to be opposite of me. All right, so let's look at all these scenarios real quick. A car is moving eastward, it's speeding up from 25 to 45 miles per hour. So if I'm moving east, let's say that's east. If I'm speeding up, then the acceleration has to be in the same direction. And which way would that be? East, right? East means speeding up. If the velocity direction and the acceleration direction are the same, that means speeding up. If they're opposites, that means slowing down. So if you got the idea, this should be easy. A car is going north and skids to a stop. Skidding is slowing down, right? Skidding to a stop. If I'm going north and skidding to a stop, then my acceleration has to be which way? South, opposite. If I'm slowing down, they got to be opposite. And actually, just to save a little bit more time, the remainder of these are all slowing down situations. So we just go opposite. This one, you dive into water. Water slows you down, right? You're going down, but the water accelerates you which way? This way, and that's why it slows you down. If it went both ways, you'd speed up when you hit the water, and that doesn't happen, right? So that one was, you were going down, so the acceleration has to be upward. All the rest of these were slowing down. So whatever the directions were involved, if we jumped in onto this one right here, if we're moving rightward and slowing to a stop, the acceleration's got to be leftward. Okay? So like I said, since we're low on time, and I want to talk about some other things and recap some other things, don't worry about number 10. All right? It was the same idea, but sometimes that diagram I don't think was explained the best. Could be a tad bit confusing. All right? So that's all the most important stuff about acceleration between the notes, and especially all the ones we answered on here. I'm not trying to trick you on tomorrow's quiz, okay? I'm just trying to ask you basic questions to see if we have a basic understanding right now of the 3 big ideas. This was the third. Again, the first big idea was distance and displacement. We did a concept builder review of that earlier this week, right? And we have a study guide. Look over that first study guide. Then speed and velocity were the next big idea. We did have some calculations with V equals D over T. Like I told you, I'll give you that formula if needed. And the final thing, acceleration, this study guide. So look over those 3 things. When you get in here tomorrow, I'm just going to say go to Google Classroom. The quiz will be posted on there. Our quizzes will have a variety of different formats. So they're not always going to be Google Forms, okay? This one is, but there's not going to be tons of quizzes anyway, I told you in here, but some will be on paper still. All right, but this particular one's in the multiple choice format. 2 points apiece, 12 of them, 24 points total, okay? Just FYI, don't anybody would do this anyway, but since anytime you do take an assessment, like a test or a quiz on like Google Classroom on a Google form, I will have GoGuardian on. That's the only time we pretty much use it. And I will be able to see your screens. So don't flip back during the quiz to study guides. I'll be able to see what you're looking at. What you can have open with the quiz is a calculator on your Chromebook if you want it. If you want to split screen it, have the quiz on one side and have a calculator on the other, there will be a couple of small calculations using some of these formulas. Okay? Yeah. If you wanted scrap paper, that's fine. It's just that for sometimes some of the calculations, the numbers don't come out nice and it'll be like decimals in some cases. And that way, I mean, I normally in the past would just let you guys grab one of these calculators. They want to limit us how much stuff we pass out. So we're supposed to tell you to use the calculators on your own device. So otherwise, I know it's kind of a pain. I'd rather hand out calculators because I have them, but I'm not supposed to. But other than that, that'll become the format of it. 12 questions, multiple choice, 18 minutes should be plenty of time to take it in this short Friday. So next week, what we go on to then is going to be motion graphing. We'll probably spend a week and a half pretty much on that, give or take. Also next week, we haven't had a 5-day week of school yet. And I told you once we do start having 5-day weeks, one of the days, usually a Friday, but possibly a Thursday, we'll start building in these how stuff work assignments. They're those article summaries I talked about like the first day. They're easy points as long as you complete them. You just got to do summaries of like on this website how stuff works. And the first one we're going to do next week, late in the week, either Thursday or Friday, is going to be how a GPS works. We're all familiar with GPS, right? I mean, practically every new vehicle has one, and if you don't, you have it on your phone, right? Just to get an understanding of that, because GPS has tons to do with what we're talking about. When you're using a GPS, it's tracking your distance and displacement, right? It's also tracking how fast you're going. Many of them, even though you have a speedometer in your vehicle, many GPS receivers, especially ones that are built into cars, also tell you how fast you're going. So the satellites themselves can tell how fast you're going and record that to you. So that has to do with distance, displacement, speed, velocity. But we'll look a little further reading a pretty easy to understand article. Well, how in the heck is it able to actually do that? So every time we do these how stuff works, they're usually related to something we just did or are going to do. And like there's some really technology related and stuff like that somehow applies to what we've been doing. All right, so anyways, we only got a few minutes. Does anybody have a question on anything on the quiz? I don't try to make up questions that are trying to trick you. I just take the things we stress the most, the biggest topics that I told you it's on, and put similar questions on it. That's all. All right. We got less than 2 minutes, so if there's not any questions, I will stop there.